Good morning, everyone. Thank you. Glad to be coming here to Germany and to CEBIT to talk about the future. 2 years ago, I was talking about how our life is going to be shaped by 5G. And last year, I was talking about the age of the intelligence machine. Today, I want to talk about something that I think it could be one of the most transformational revolutions in our lifetime, and this is the renaissance of compute. Now, many of us in the industry have seen this renaissance already going, and the real question is, what is igniting it? One irresistible and overwhelming force, data. And as you can see, the world is basically already struggling with the unprecedented amount of volume of data. Humans are creating informations, photos, videos, and sharing many more of data forms. With machine-to-machine communications, we are expected to see even more overwhelming richness of information. And the amount of computer power that will be needed to generate this data is huge, and it's only going to get bigger. Now, but first, let me take you back and to show you how all of this data is going to change the way we think about what compute means. Now, we already know that our life in computing is already smart and connected. But unfortunately, this is still the same as decades ago. The data is static, siloed, monolithic, and generic. And I say that without an apology. I really had the privilege in the past 20+ years to be part of the people who define these architectures and deliver it into our systems. CPU performance has become better and better and getting more performance and more compute power. Now, will tomorrow compute engines will be faster? Yes. Will be smarter? Absolutely. But what I'm talking about, that compute of the tomorrow will have to be specialized and constantly learning from its environment. Why is that so important? I think this is important because data as data can no longer be static. We will not just be storing data, transferring data. We're going to live in a world where all of our computing around us will be engaged in real-life activities and cycles of information analysis, watching, learning, imitating, analyzing, even thinking. This is the world of computing that we're about to enter. And since the invention of the abacus thousands of years ago, transformation has been fueled by computations and vice versa. As you can see in the screen on the high level, technology moved along two specific vectors: disruptive capabilities and more compute capabilities, which fed on each other. The Turing machine, for example, from the 1930s that you can see here along the bottom axis, was a perfect example when a desperate need to crack the Nazi code had led to disruptive computing capabilities. And that is also true to some of the other revolutions, such as mainframe computing, personal computing, multimedia, smartphones, and autonomous machines. And as we're looking into the thirst of computing capabilities, obviously kept growing and growing. But in the last few years, there is a big change. As you can see, whether it's robotics or virtual networks, and there are more things that are coming, there is a need to go beyond performance. There is a need to go beyond of just compute power and performance power. Machine learning, robotics, autonomous driving cars, and more are illustrating that need. So I want to share with you some of the emerging disruptive compute capabilities that are delivering more of the things that are needed. And I listed just a few here, and I want to walk you through each of those just to get your imagination to follow. I'll start by the one in front of me, extracting wisdom from data. And as you know, for decades, the human interactions and understanding emotions is and was a deeply emotional and personal experiences. You had to be in front of a person to really understand how they felt, what their behavior is, and it was uniquely human experience. Now, But the computers of today, what about their ability to understand the human face? Not just to recognize the faces as they do today, not just to recognize who is the person in low light, but to recognize emotions, know the difference between their moods. Are they laughing? Are they upset? What does it really tell us? And this basically leap to something totally new. The computing model that I'm talking about would require to accumulate and to act upon multiple layers of neural networks data. They can identify subjects based on facials and body recognitions and allow us to interact from all angles. That suggests a computer that needs to do more than just calculate and compute. We're talking about something that can draw inferences or reach conclusions on their own. In fact, everything that we're turning into data. And I mean everything. Pictures, voices, noises, streetlights, movement, musics, videos, all is converted into data that needs to be augmented and understood by computers. Now imagine this. Billions of cameras are capturing everything from traffic light to human interactions, compiling and sorting it all. In this world, we are demanding computers to do something different. We need computers to help us more than just capture, store, and transfer the information. We need to analyze. We need to synthesize. We need to make sense of all of the data that we're accumulating, to comprehend the symbolic meaning of everything, to understand the impacts of minute changes in telemetry, and to make real-time decisions, and to understand the machinery or even human movements. I want to talk about how video is so important to our life. And you know, in fact, the surge in video amplifies the fact that video is the new voice. YouTube, for example, is not just a place where to share videos. This is where people basically explore their experiences. And video is not just the commonwealth of the millennials. In fact, many of factories around us, buildings and others, are already starting to incorporate videos in everything that they do. In business, in factory settings, this is important because basically it's becoming from a tool of just capturing and monitoring to something that you should consider as always on. And this always on is just the beginning, because the way we see it, videos will be basically escalating, demanding data, and expected not just to be on one element, but through the edge perspective, to become live in any network, in any edge device, at any venue, at all at the same time, with low latency. It requires us a system that knows how to encode, decode, and transcode, and everything with an instant zero low latency. This is a huge task. Now let's talk about hurricanes. In 2017 alone, in the United States, the damage for hurricanes was more than $300 billion. One hurricane alone, Harvey, totaled more than $175 billion in damage, not to mention the loss of life. Unfortunately, our computing systems are failing us. They're unable to predict. They're unable to understand real-time movements. As I was talking about data in the previous examples, here the challenge is different. How should we draw conclusions based on a very limited data? What should we do in order to assess the situation in uncertainty? That's one of the promises of new age of computing, and I'll get back to that. The next example is when real and virtual reality blends together. This is already happening in streets around us. And you can see it as in the crowded cities, we're already starting to have security cameras and a lot of sensors around us, whether it's on cars, on people, on poles, light stands and others that are aggregating and compiling everything. And the result is augmented reality at its best practical form. And it's almost like you assessed it on the go. That requires us the capability to have embedded 3D rich media and to take ourselves to the next level. Think about applications such as Waze or Google Maps. These are pretty much static applications, emerged with real-time sensory and understanding of the capabilities bring us to the next level. It requires a new type of compute engine at the edge with a very low power. We want something that brings mobile experiences alive. But that experience is not only on the go. In the home today, we're already starting to reflect the changing environment with the computers, from merely a personal assistant to understanding companionship. Computers are already responding to voice commands or typed instructions, but the always watching, always thinking compute models shifts the possibilities. Instead of just waiting for a voice command, the new computer will be something like you know very well. It will infer from your voice. It will detect the mood that you have and play the right music. It will understand when your dog needs to be fed or needs to be let outside and maybe needs to be pet. All of this basically requires non-traditional compute engines. These will be based on networks that will observe constantly and understand and sense and respond to sources of information, like becoming your best friend around you. And finally, there is the one that all the computing engines we've been looking for. It's the time when machines learn to think. When I say thinking, I mean the ability for robots, drones, autonomous cars, and other machines to interact among humans and among themselves. These machines do not just collect sensory items. They process layers and layers of data and the information in order for them to make decisions, to use judgment, to make predictions, to draw conclusions, and more importantly, act on their own. Now, you may think that this is basically a science fiction, but in fact, we are already seeing it. And this is what we're asking autonomous machines to do. To achieve all of this, we need to be delivering more advanced compute engines that can actually process and deliver more of just compute power and compute performance. We need something that knows how to make the sense of it. And I call that meaningful compute. The examples that I've shared with you with emerging disruptive capabilities are just a few. There are others, and there will be plenty more. But unfortunately, the computer model of today is designed today around computation, and it doesn't do it good justice. We need something more dramatic that can deliver something more than just compute power, compute performance, smaller size. And I call it meaningful compute because it delivers something in the different vectors beyond of the things that I described. For instance, sentimental, which basically anticipates and responds to human experience with data, a computer that can understand our emotions and how do we feel, how do we interact. Cinematic, remember I was talking about the surge of video, a computer that basically can deliver and all the videos around us to do all the power and just to computer elements on decoding and encoding, analyzing, rendering, synthesizing, and sharing on an instant. I'm talking about contextual inputs that allows the computer to assess the situation, to understand what is the right response in any given time. And last but not least, metaphorical. It's basically we want computers to respond to us based on our deep knowledge of understanding, whether these computers are based on instant layers of understanding immediately or draw conclusions from past behaviors. Now, these disruptive capabilities will continue to evolve, of course. And my point is that for the next stage of computers that needs to be measured, not just by how much compute power or computation they can perform, but also in new levels of meaning, and meaning that can be actually extrapolated into inputs like the old primitive, like compute engines used to do. And I think when you look at that and you think about it, and it sounds like a science fiction, in fact, all of our history, when we developed technology, was filled with anxiety and fears. Let's watch the following movie.
I heard you go too fast and you'll melt.
Electricity. I'm not putting lightning in my walls.
I'll leave flying to the birds.
You know, it mutates all the nutrients in your food.
They have these little soaps there that I can't find anywhere else. Oh, my hands smell amazing.
Do you really need to talk to people all the time?
Soon, artificial intelligence will be able to flag a health issue before you even come for a checkup.
Yeah, I don't need a machine to tell me how to live. Ooh, I'm gonna be late for a meeting.
Intel is powering artificial intelligence that can help doctors save lives. Don't worry, we'll help you get there.
So as you can see, basically, the question is, how do we overcome a persistent doubt? How do we make all of this happen? Now, the good news, we are already making it happen. And I wanted to illustrate and just to share with you a few examples. How do we evolve the new compute engines? Let's share the 3 examples. The first one, and the most profound one of a new compute engine, it's about deep learning. It's a system that has the ability to recognize objects, voices, and patterns with a very low power. And the chart here tries to understand the differences. Under the traditional computing model, object recognition requires us to program the machine way in advance. We have to understand the algorithms that are specifically designed to look for certain characteristics, whether size, edges, colors, distance, and others. And then each object has its own algorithm, and the machine runs a certain level to try to find the accuracy in order to infer the conclusions. This is impressive, however, it's very difficult to scale and takes a lot of power. On the other hand, a deep learning neural networks takes a very different approach. Here, as you can see, we're teaching the computers to understand and to make inferences by mimicking some of the brain functions that we have. And in order to understand, is that a human or a bicycle or strawberry? Instead of building an algorithm for each object, the deep learning mechanism basically uses arrays of multipliers, and each of them is basically allows us to draw different inferences. So what we do, we train the machines based on running multiple images, and then they learn to identify whether it's a human or strawberry or different objects. Eventually, it immediately can tell us whether they identify, in case of the bicycle, if it's a seat or spokes or other element that is recognized as a bicycle, to defer and to determine the same characteristic as a bicycle. And the good news, the more calculation, the more successive elements the network is performing, the more capabilities will be retained for the next calculations. So this is quite impressive. And I think that neural network agents will be a subset of almost every compute engine that we're going to design. And remember, I was talking about the video surge and what do we need in order to address the challenges. On the left side, you see what we are doing today with computers. We capture an image, and then we ask the computer to improve it. And on the right, you could see multiple of new elements that are coming to play. We take ourselves into a positions where we use multiple engines to try to build volumetric data, to conclude and to create syntheses based on data that does not exist. We're moving from an 8G resolution to something that we call super resolution, where computers are adding additional information based on preset of characteristics that are neurally defined. We're looking into situations when you're looking to blur an element to make a synthesis of the goldfinch bird that you're looking to identify. All of that requires tons of intuitions and requires the compute engines to supplement the digital data, what I was referring earlier as static data, and to draw instant, immediate, dynamic conclusions. And as we look into robots and drones and autonomous cars, we're looking into taking sensory to the next level. What we need is basically something that will fuse more on the senses that we know today, more than just the 5 sensors that human being is capable to correspond to. And that requires us to create a different relationship with our compute capabilities. When we fuse some of these sensors, and I've just listed a few into ones, every robot will have multiple sensors to control. And the movement and the preparation for basically this sensory array to interact with other humans and other drones, other robots, will becoming very, very critical. These capabilities require us not just to fuse them together, but when you're looking into edge devices, when you're looking into something that operates in our environment without power cords, we need to detect new compute engines that know how to operate in different voltage level that we are recognized as of today. In the next stage, basically we would have to operate not just by a push of a button or basically drawing a keystroke. What we're asking these machines to do is to interact and to retain enough information they will be able to harmonize the data and to move around us. And as mentioned earlier, we're already working on certain of these capabilities, and we're starting to deploy those. I think at the end of the day, these compute engines will have to work all very fluidly, autonomously, and without the need of having human intervention. Now, as I share with you, these are some of the compute engines that are being built. But the problem that I've described to you already is that still, even with these compute engines that I've described, it's kind of an evolutionary step. I wanted also to share with you what lies ahead, what we do at Intel in our labs and some of the academias to do more dramatic moves to really grasp the future when the future lies ahead, whether it's 10, 20, 50 years from now. Something that will give us a more bold glimpse into the future. Let's take a look. I would like to start with what we call probabilistic computing. Now, today, computing models are doing quite well with a yes or a no. The computers of today don't know how to work the programming model with a maybe. And this is where probabilistic kicks in. The current approach deals with that, is utilizing some software tricks, but this is clumsy. It's not operating well and not power efficient. So we need to define better models. Better models, for example, that we know how to deal with noisy environment using intuition. What we're trying in all of these examples, we're trying to mimic the human brain. Now imagine a robot walking in your home in a noisy environment. There are some other robots or other humans, it's a low light, people are talking, and it needs to pick up the signals and to maneuver and to do the tasks. That's a probabilistic computing. Imagine that some of these calculations will have to be already hard-coded in hardware, rather than to be coded in software. So that boosts our possibilities immensely. It takes us to a new dimension where basically we're adding the maybe into that construct. And inside of the academia and in our labs, we're already working on some of these models. I also want to talk about the interactions with biological computing. And computing has so much to learn from the science of the DNA. As many of us know, the design of a human being or all of the living around us is basically coded in a simple formula of ATGC. This is basically an entire sequence that delivers so much information with such resiliency. The DNA that we know exceeds by far all of the traditional computing that we know. Because of this DNA resiliency, we can do quite a lot. I want to share with you one example. When scientists studied the prehistoric DNA of the woolly mammoth that was found under the ice, they estimated that 1 gram of DNA contained more than 215 petabytes of information. And it was done probably more than 400,000 years ago. Now, that's a resiliency that we should mimic, right? So if you think about a traditional computing model, we need to do something different. We need to use biological data and to create data factories that can transfer and create the information from one cell to the others. Instead of building a computer, we will just grow one. The next example is quantum computing. Now, this is a very cool and exciting domain, because if traditional computing, you can defer, is basically the speed of sound, in quantum computing, you have to think about it like it's running on the speed of light. In traditional computing, we can actually create bits that are either storing values of 0 or 1. In quantum computing, basically we're replacing the bits with qubits. Each qubits represent a full array of possibilities between 0 and 1. And when it integrates simultaneously, it can create an overwhelming explosion capabilities of calculation at the same time. And that's something that requires us to define and to create additional breakthroughs in order to create the possibilities to take advantage of these calculations, all on the same time. These breakthroughs are reminding me some of these elements when we started to work on high-performance computing, because this type of calculations will allow us to create some major breakthroughs when it comes to chemicals, drug development, molecular. The imagination really takes a big hike here. And I think that quantum computing, although very nascent, has tremendous capabilities and opportunities. Now, I do want to put a word of caution. Although Intel has introduced 49 qubits and few others are also trying to introduce those machines, we're far away from completing this journey. There's tons of challenges, whether these are scalability, power, thermals, capability to contain the information and to access and read it while computing. But the imagination to do around it is unbelievably compelling. And last but not least, I want to talk about what we call neuromorphic computing. This machine, this computer, will allow us to replicate another very good decision-making machine. Guess what? It's the human brain. If you think about it, today, our models, our machines today are running, right? If you think about being operated by a clock that basically coordinate all of the activities, we're relying on high accuracy, and we need sometimes kind of milliseconds in tens of hundreds of watts to operate. The human brain, in comparison, takes something like 20 watts, and when we sleep, it goes even to 8 watts, etc. It's one of the most, actually the most effective compute machine that we know of today. It runs on neurons connecting into synapses. And all of this ignites the possibilities if we can mimic the human brain. And at Intel, we have developed a research neuromorphic chip by the code name Loihi, which basically, by the way, it's a volcano about to be erupted around the water of Hawaii, if you guess what is Loihi is. And the really interesting, impressive element about Loihi, it is already today, it delivers more than 130,000 of neurons connecting to 168 millions of synapses. Now, as impressive as it sounds, it is not a fair comparison. It's about the half of a brain of an ant. Okay? So we have a way to go. But other than me talking about that, let's hear what our folks in Intel Labs are capable to share with.
Traditional computing rests on this basic idea of you have two computing elements, a CPU and a memory. And neuromorphic computing is throwing that out and starting from a completely different point on the architectural spectrum.
Our own brains are remarkable in what they can do. We're simply trying to learn from what our brains, the brains of animals, can do to make systems that are smarter and more efficient.
What we're looking for is to connect all of the neurons in the chip, much like we would with an actual brain. So neuromorphic computing is basically the concept that we're going to simulate the brain in silicon.
Neuromorphic computing will show up where they find an application that benefits from being able to embed the intelligence into a device, initially in areas of robotics, autonomous vehicles, where the power and the size and the adaptability are really beneficial.
There's a number of different ways it can go, and we can see it filling out the whole extent of machine learning as people have envisioned. So it's a generalization of computer architecture to really provide the right tool to implement artificial intelligence.
What Luigi provides is just like your brain. It's going to connect up neurons to get together, and the way your brain learns is it changes the connectivity between your neurons. What Luigi gives you is the capability to build a network, and then you feed in data, and then it will change the network as you're going and learning, and then we'll tell you what the result is online, at the edge, in low power.
It's really fun to be a part of a project where we have the strength of a company like Intel to invest in these areas and to really solve these hard problems with the whole portfolio of great technology and talent. And neuromorphic computing is an extremely hard problem, but it's one that Intel's scale and expertise can really be brought to bear and make a real difference in the industry and for the world.
So in conclusions, as I share with you today, the renaissance of compute is more than just a new compute engine or a new machine. It is above all about the possibilities. We are in the midst of one of the most exciting periods of our lifetime, when the capabilities for emerging disruptive elements are bursting, and we have the advantage to basically take ourselves into new domains. My advice to my colleagues and my advice to you guys, keep focused in the emerging capabilities, because this is where the next innovation is going to come from. Thank you so much, and enjoy the rest of the conference here at CEBIT.
Thank you, Amir. Just one question, since we're running out of time a little bit. This neuro-machine computing, how far out is it? Like 10 years to go, 5?
Well, we already have something that works today. So we're opening it up selectively to some of the research institutions that they can run the programming model.
So academia can use it right now. We'll see about the rest.
Hopefully in 10 years, when you and I are coming back to this stage, we'll have small robots to round around us using this machine.
Okay, maybe we need them. Thank you so much, Amir.
Sure.
Thank you.
Thank you.
Bye-bye.
Thank you, guys.